Now that we're talking about describing curves in R2 and curves in R3, we can start with a nice simple shape for R3. We're going to talk about lines in R3. Now, this is going to be different from linear equations in R3. We know that if we take a linear equation in R3, let's say some delta x times x minus x naught plus delta y times y minus y naught plus delta z times z minus z naught equals 0. We know that if we take a linear equation in R3, we don't get a line, we get a plane. We know that when we're looking at the equation of a plane, we're going to be looking at a plane containing a point with a normal vector. So the coefficients, they don't tell us the slope, like in y equals mx plus b. They tell us the coordinates of the vector normal to the plane. We also saw that if we looked at lines in R2, in standard the standard equation of a line, the coefficients represent the coordinates of a vector normal to the slope. Well, when we look at this information, it's a linear equation because x, y, and z are all degree 1. All the terms are degree 1 or less. And the information is containing a point normal to a given vector, plane normal to the normal vector. But we don't want to describe a plane in R3. We want to describe a one-dimensional line in R3. So this is a plane in R3, and that's a two-dimensional thing. So the plane is two-dimensional. Two-dimensional plane in R3 containing this point and a normal vector. But what we want is to describe a one-dimensional line in R3. That's what we want to do. If I take a piece of string and tape it to the floor in this corner and then tape it to the ceiling up in that corner, I want to be able to describe what the equation, I want a set of equations for that piece of string. I want to describe that one-dimensional line in three-dimensional space. One of the ways that we already do this is with vectors. We say, given a starting vector and going in a particular direction. So we're going to start by using vectors. We're going to say there can be a line in R3 through the vector, through a starting vector, and in it with a direction vector. So I'm just going to write it out. So here's how we can write the equation of a line in R3. So here we could write a vector. We could write this combination of vectors to represent a line in R3. I like to start with this because this looks very much like a linear equation in two variables, where P is like the y-intercept and V is like the slope. But now, since we have vectors P and V, we can describe a one-dimensional line in three-dimensional space. So when we have the origin out here somewhere, we have our fixed vector P. And then to this vector P, we add all the multiples of a vector V. So that's going to give us some kind of direction. So along this line are all the multiples of the vector V. P plus 0V will be right at this endpoint, right at this starting point. So this point here will be P plus 0V. It's not a just be your starting point. Just like y equals b plus mx. When x is 0, y is equal to b. V is headed off in this direction. So at this point here, we'll have the point P plus 1V. I'll take another copy of the vector V. Here we'll be at the point P plus 2V. If we want to get the line on the other side, we just have negative values of t. So that P determines a starting point and V determines a direction, just like we know linear equations are supposed to do. We have a starting point plus a direction. We're looking at a starting point plus a variable times a direction. So the starting point plus some variable times a direction. There's a starting point plus a variable times a direction. Start at B and add M a bunch of times. Start at the vector P and add the vector V a bunch of times. Make it fit the format that I made up before. I had it the way I wanted it. It's the previous one that's backwards. Yikes. That's what happens when I try to make things line up. So we have a start plus a variable times a direction. Y starts at the value of B and increases by M a bunch of times. Or we start at the point P and go in the direction of B a bunch of times. Any questions? Everybody okay? Yeah, it's linear equations. We got this. Well, it's not quite just a linear equation. Got to bring vectors in. So let's look at an example. So if we want to find the equation of line containing these points, 2, -1, 3, and 5, 3, 1, we need to figure out, we can take either one of these points as our starting point. We don't have a y-intercept like we do in the linear equation. That's one of our differences, y equals mx plus b. So either one of these could be our starting point. We need some way to describe the direction. And the direction, we just go from one point to the other. How much of a change is there? So our direction vector it looks like if we start at 2 and end up at 5, we increase by 3. If we start off at 1 and end up at 3, we have increased by 4. And if we start off at 3 and end up at 1, we have decreased by 2. We just look at what happened. So if we think of 2, -1, 3 as the start and 5, 3, 1 as the end, I did 5 minus 2, 3 minus a -1, and 1 minus 3. So I just did 5 minus 2, 3 minus a -1, and 1 minus 3. This isn't the only vector. I just said the one on the left was the start and the one on the right was the end. Another candidate for describing the direction describing the vector in the direction of these of the line containing these 2 points is to go the other direction. Instead of 5 minus 2, do 2 minus 5. But these are just going in opposite directions. V1 is just -1 times V2. I can use either one of these points as a starting point. So I could say it's 2, -1, 3 plus t times 3, 4, -2. For 2, 1, -3, I could replace that with the other point that I know about, 5, 3, 1. For the direction vector, if I just flip the t on in the other direction, for the direction vector, I could just use the opposite. The direction vector is just a direction, and we're going to be writing all of the values of t. So I can actually use any multiple of these vectors. I can use any multiple of 3, 4, -2. I can use 30, 40, -20. Depending on the values of t I want to use, I can use whatever I want. All I care about is the ratio of the I, j, and k components. We already do this because we know that in the equation y equals mx plus b, m is just the ratio of the change in y divided by the change in x. So what's important is the ratio. But now we have 3, so we don't have a 3-way fraction to make a ratio out of. So instead of change in y divided by change in x, I just do change in x, comma, change in y, comma, change in z. So we're not doing anything different. We're just organizing it differently because we have more information to communicate. Good question. Really, the equation b plus x times m, we could think of that as the vector 0b plus x times the vector delta x, delta y. Because in that situation, we only have 2 coordinates for our vector, delta x and delta y, we put those together in a slope. And then it's rise over run, and people be like all up and over. And I'm like, all over is not a direction. Seriously, being in my algebra class is super annoying because you'll be like all up 5 and over 2. And I always go the wrong direction. So I'm like, well, tell me what the next point is. Go up 5 and over 2. Oh, that's the wrong line. They're like, oh, lead you, Dick, you know what I meant? Go to the right. Oh. Because, yeah, I did know. But I want to remove all down. So say up 5 and right 2. Or if you want to be different, down 5 and left 2. But if you're going to be different like that, you got to make sure that you kind of sound a little bit snotty about it, like little man Tate. You have to be like distracted, not paying attention. Just be like, oh, all of them. Even though little man Tate is like super wrong in that scene. I might be remembering that whole scene incorrectly because I haven't seen that movie. There's a lot of movies where math stuff happens and I just haven't seen them. Like Good Will Hunting, I haven't seen that movie. A lot of movies where they're math adjacent, but they're not math movies. It's like Good Will Hunting. Yeah, they chose to use mathematics for I guess his name must be Will Hunting, right? Which is super cheesy. But anyway, they use math to demonstrate how smart he is. But it really could have been anything. Well, a limited scope of things. But you wanted him to seem incomprehensibly smart. And so they made it math. Anytime you want your character to be incomprehensibly smart, make them mathematicians. Being a mathematician doesn't make you incomprehensibly smart. I mean, counterexample sitting right in front of you. But it's a way that an author can communicate incomprehensible intelligence. That's how you make a wizard in real life. He's a mathematician or a theoretical physicist. Like, oh, wow, that must be complicated. Then, of course, we just go around telling people that it is. We kind of maintain that assumption. You know what I mean? But it wasn't a math movie. Same thing with the kind of beats everybody up. Gladiator. Anyway, same with Gladiator. That was not a movie that was about math. It was a movie about a mathematician. But it's most definitely not telling the story of his math. You know what I mean? Except for the one scene, which reminds us that he got a Nobel Prize for saying, we'd all be better off if we would cooperate. And we're like, oh, yeah, we should all cooperate. Nobel Prize for this fucker. And then what do? Go right back to competition. I guess I'd lose my mind too. Yes, we should all cooperate. High five. That is correct answer. So you got to implement those policies? Nope. The owners have said they need people in poverty. You know what I mean? Anyway, I can't even remember what was that movie called? A Beautiful Mind. That's what it was. If you haven't seen it, you should go see it. Russell Crowe, that's his name. So if you want to see Gladiator do math instead of stab people, A Beautiful Mind. What are we talking about? Oh, yes. So we've got this vector equation. Now, we might be noticing, dude, you were talking about parametric equations, and now we've got these vector equations. And this is a parametric equation. Our parameter is right here, it's t. If we just break this up into components using scalar multiplication and vector addition, that will give us the parametric equations of this line. If we just add these two, if we just multiply and add, we'll get the vector 2 plus 3t, negative 1 plus 4t, 3 minus 2t. What we're looking for in parametric equations is a function for x, a function for y, and a function for z, and there they are. Function for x, function for y, function for z. Any questions? This does add something because we were switching to parameterized lines. This does add something. So from the but wait, there's more file. Remember that a parameterized curve has a direction. Parameterized curves have a direction or an orientation, a place to start and a direction to go. So we can take this line and we can make create different describe different segments depending on our control of the value of t. Now we can change the direction based on where we start and where we end. So for example, we can start at -1, 3 and end at 5, 3, 1. So the direction that we're assigning a direction by saying, here's our starting point. This should be what happens when t is equal to 0. And we should be at 5, 3, 1 by the time t is equal to, let's say, 1. So when t is equal to 0, we want to make sure we have 2, -1, 3. And when t is equal to 1, we want to make sure we have 5, 3, 1. So our equations are just like we had above. And to make sure that we start off at, in this description, t will start off at 0 and end at 1. And that will be just the segment from 2, -1, 3 That'll take us from t equals 0 to t equals 1. When t is equal to 0, we get 2, 1, 3. When t is equal to 1, we have 2 and 3 is 5. -1 and 4 is 3. 3 minus 2 is 1. And in this here we have starting at 2, -1, 3 and ending at 5, 3, 1. If we want to reverse the direction, I could just write a new set of equations. I could just say x is 5 minus 3t. Y is 3 minus 4t. And z is 1 plus 3 plus 2t. In this case, when t is equal to 0, I'm at 5, 3, 1. And when t is equal to 1, I'll be at 2, negative 1, 3. So I've changed the direction of my segment. I'm still connecting the same 2 points. But now the direction is reversed, because t equals 0 corresponds to 5, 3, 1, and t is equal to 1 corresponds to 2, negative 1, 3. Questions? If we're given 2 points and we want to write the equation, then we should just make the distance between the 2 points 1 unit in the parameter, because that makes our life easy. But let's suppose we're at 5, 3, 1 when t is equal to 0, and at 2, negative 1, 3 when t is equal to 7. So I don't want to make this jump in 1, whatever units t is, but I say that takes 7 units of t. So I don't want to subtract 3 every 1 unit. I want to subtract 3 every 7 units. So what the t equals 7, t goes from 0 to 7 instead of from 0 to 1. That means we're changing our, if we think in terms of y equals mx plus b and rise and run, we're changing the run from 1 to a run of 7. So I don't want to subtract an entire 3 until t has gone through 7 units. So when t is equal to 0, we're at 5, 3, and 1 like we wanted. And we don't subtract an entire 3 from the 5 until t is equal to 7. We don't subtract 4 from 3 until t is equal to 7. And we don't add 2 to the 1 until t is equal to 7. So now I've got the same segment. We just slowed it down a little bit. Now, instead of starting off when t is equal to 0 at 5, 3, 1, and then getting to t 2, negative 1, 3 in 1 unit, now it takes 7 units. And we are playing the same rise over run game that we were playing before. How much is each of the X, Y, and Z changing? We're just looking at delta Y over delta X over delta T, delta Y over delta T, and delta Z over delta T. Why we like linear equations and describing lines, it's so simple. We need a starting point and a direction. And the direction can be in any ratio. How's everybody okay? Oh, I forgot to mark the direction. Last thing. What happens if we substitute, replace the little lowercase t with 7 minus t? So substitute t equals 7 minus capital T into that set of equations for t between 0 and 7. What's going to happen when I replace t from 0 to 7 with 7 minus capital T or capital T from 0 to 7? What will happen? Take a guess at what would happen. And then, since I've given you an explicit instruction to follow, just do that and follow your nose and then read what happens at the end. We'll talk about that tomorrow, but today was all about parameterizing a line. We're trying to describe a line in R3 because we can't use a linear equation in 3 variables to do it. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.